Let's do another example where we're projecting something and it lands at a different level. And we'll also figure out some other interesting things. We'll figure out what the actual velocity vector is when it's landing. So both its magnitude and its direction. So let's do a situation. So let's say we're launching something from ground level. And we're going to launch it at a pretty steep angle over here. So let's say we launch it with an angle. Let's say we launch it with an angle of, let's say it's 80 degrees. We launch it with at an 80-degree angle we launch it at an 80-degree angle, and it is going to be going at 30 meters per second. 30 meters per second. So that's the length of this vector. That's the magnitude of that vector. And let's say we want to make it land on this landing. And this landing right over here has a height. This landing over here has a height of 10 meters. This height over here is 10 meters. So what I want to do first of all is I want to figure out how far along the landing do I actually land? How far along the landing? So, and maybe I'll add some other information right here. So say from this launching point to the beginning of the landing, let's say that this right over here is 2 meters. 2 meters. So we just want to know how far along the landing do we land. So like we did before, we want to break this vector into its horizontal and vertical components. And I'm going to go a little bit faster in this video because hopefully we're getting the knack for this type of thing. So our velocity in the vertical, or our vertical component of our velocity, is going to be equal to the magnitude of our total velocity, 30 meters per second, times, and it's going to be the sine of 80 degrees, because sine is opposite over hypotenuse, times the sine of 80 degrees. And we'll just get it out of the way right now, the horizontal component of our velocity is going to be 30 meters per second. And I'm not writing the units here just to save some space, times the cosine of 80 degrees. Once again, cosine is adjacent over hypotenuse. And if you feel like I'm skipping steps, in the last few videos I go into this into much more detail. So how much time do we spend in the air? How much time do we spend in the air? So once again, in the last few videos, we saw that we can look at displacement. If we want to figure out time in the air, we know that displacement is equal to the initial velocity times time, plus acceleration. Let me write times change in time, since that's more technically more correct. Plus acceleration times change in time squared over 2. Now, in our situation, we know what our initial velocity is. We're talking about the vertical direction right over here. So our initial velocity is going to be this. We're trying to figure out how time in the air, and the vertical component determines that. Because at some point, when it hits back to the ground, it's not going to be traveling anymore. So that's what's determining its time in the air. So we know that. We know the acceleration. Remember, our convention when we're dealing with the vertical dimension is up is positive, down is negative. So this is negative 9.8 meters per second squared. And then what is the total displacement that we're going to have? Well, we're starting at ground level, and we're just talking about the vertical. Remember that. So our total displacement is going to be 10 meters. So this value right here is going to be 10 meters. So it simplifies to 10 meters. I won't write the units here. Is equals 10 is equal to, what's 30 sine of 80 degrees? So we have 30 times the sine of 80 degrees gives us 29.54. 29.54. So this is 29.54 times our change in time, And so this is negative 9.8 divided by 2. So it's negative, I'll do that same green color, that's not the same green color, negative 4.9 meters per second squared. I'm not writing the units here, times delta t squared. And then we could subtract 10 from both sides and write this in a traditional quadratic equation form. So we get negative, and I'm going to flip the sides too, negative 4.9 times delta t squared. And then we have plus 29.54 times delta t minus 10. Minus 10 is equal to 0. And then we can use the quadratic formula to find the roots of this. So the delta t's that satisfy this quadratic equation are going to be negative b, so negative 29.54 plus or minus the square root of 29.54 squared, b squared, minus 4 times a, which is negative 4.9. So the negative times the negative is a positive. So it's plus 4 times positive 4.9 times, well, I shouldn't have jumped so fast to get rid of the negative. So it's going to be minus 4 times a, which is negative 4.9, times c, which is negative 10. So just a times c, negative 4.9 times negative 10. So let me just write negative 4.9 times negative 10. These two guys, their signs are going to cancel out. All of that over 2a. All of that over negative 4.9 times 2, so negative 9.8. And like we saw in the last video, we want a positive value for this. A negative time is nonsensical. That's kind of going into the past. So we want a positive value. And since we have a negative in the denominator, we want to have a negative value up here. And if we already have a negative value here, if we subtract from that negative value, we're definitely going to have a negative value up here. And then you divide by a negative value, you'll get a positive value. So we can really focus on the subtracting the radical. And you could try it out. If you try the positive version, you're going to get a negative value for this entire thing. Do that on, you could try that out after this video, just to verify that you'll get a nonsensical answer. So let's use the negative right over here. So we have negative 29.54 minus the square root of 29.54 squared. And then we have minus 4 times negative 4.9 times negative 10. These two, when you take their product, is positive 49. So times 49, and I should add a parentheses over there. So let me insert a parentheses. I can insert parentheses. Okay. So times 49. So this right here will give me the numerator if I evaluate this. Got me a negative value, and then I divide that by negative 9.8. So divided by negative 9.8 gives me 5.67 seconds. This is equal to 5.67 seconds. And you could keep the units in there and make sure that all of the dimensional analysis works, and I think you'll find that it does. So the total time in the air is 5.6. The total time in the air is 5.67 seconds. Now, what I want to do, the whole point of this is to figure out how far along this landing we land. Well, our horizontal component of our velocity is right over here. We know that our displacement in the horizontal direction, will be our velocity in the horizontal direction. And it's a constant velocity, so it's the same thing as our average velocity in the horizontal direction, times the change in time. Well, the change in time is, so I'll just write it out, times our change in time. So this is going to be equal to 30 cosine of 80 degrees. 30 cosine of 80 degrees times 5.67 seconds. Times 5.67 seconds. And this, I won't write the units. This is meters per second times seconds. It'll give us an answer in meters. So once again, we have, this is our time. This is the 5.67 times 30 cosine of 80 degrees gives us 29.53 meters. So our total horizontal traveling displacement, I guess we could say, is 29.53 meters. 29.53 meters. And I'll write this as a vector. That is our horizontal displacement. It's equal to 29.53 meters. Now, we've done a lot of deconstructing vectors. What I thought would be interesting in this video is to construct a vector. So we know our horizontal displacement. We also know our vertical displacement. It's positive 10 meters. So what's our total displacement? Let me write this down. So we have a horizontal displacement. Of 29.53 meters. And we have a vertical displacement of plus 10 meters. We have a vertical displacement of positive 10 meters. And so what is our total displacement? what is our total displacement going to be? Well, we could use the Pythagorean theorem now here. The square of the magnitude of our total displacement is going to be equal to the sum of these two squares. Or another way, this is just the Pythagorean theorem. So we could have, if we call this length over here c, or let me just write it. This is the magnitude of our displacement right over here. The magnitude of our total displacement squared is going to be equal to 10 squared plus 29.53 squared. So it's going to be 10 squared plus 29.53 squared. I'm going to do that same color. Plus 29.53 squared. If we want to solve for this, we just take the square root of both sides. So I'll just do that in place. So if we just take the square root of both sides, we will get the magnitude of our total displacement. And I can get the calculator out once again to do that. So the magnitude of our total displacement is the square root of 10 squared is just 100, plus 29. I could even use, well, I could use all of this information so that I don't even lose some precision. I could say second answer. That literally means the previous answer, which is at 29.53 squared, gives us a total displacement of 31.18 meters. So this is equal to 31.18 meters. And of course, it's a vector. So we've only given you the magnitude. We also need the direction. So one way to specify a direction is to give you the angle with the horizontal. And let's call that angle theta. And once again, we can use our trig functions over here. We could use pretty much any of the trig functions. But we know the opposite side is 10. We know the hypotenuse here is 31.18. So why not use sine? Sine is opposite over hypotenuse. So we know that the sine of theta is going to be equal to 10 over 31.18. 10 over 31.18. Or if you want to solve for theta, you take the arc sine of both sides, or the inverse sine of both sides. You get theta is equal to the inverse sine, or I could write arc sine over here, of 10 over 31.8. 10 over 31.18, I should say. So let's once again get the calculator out to figure out that value. So I'm going to take the inverse sine. Once again, this is the same thing as the arc sine. This says, give me the angle that when I take its sine, I get this value right over here. So the inverse sine of 10 divided by our previous answer, 31.18. I'll just say our previous answer is equal to, so this says, give me the angle whose sine is 10 over 31.18. So I have 18.7 degrees, or 18.71 degrees. So this is equal to 18.71 degrees. 18.71 degrees above the horizontal. So here we've constructed a vector. We took its vertical component and its horizontal component, and we were able to figure out the total vector. So this projectile in this situation is going, its total displacement. So just to make it clear, its path will look something like this. Its path will look something like this. Its path is going to look something like this. And we've just calculated its total displacement. Its total displacement is 31.18 meters, 18.71 degrees above the horizontal. Now, the other thing I realized that when I started this problem, I asked you, I think I was asking you, how far along the platform? And we figured out its total horizontal displacement. So if you want to know how far along the platform starts 2 meters to the right. So it's really 27.53 meters along the platform is where it lands.